Welcome back. So we're going to continue to work with the same set of data that we've been working with, which is thinking about the cost of housing across 50 states as a function of decade. And again, just so we're all on the same page, this is the data set that we have been dealing with. So we have all the states, and then for each state, we have a series of median house prices for different decades. What we've talked about so far is that we have thought about how to plot this in a way that is more reasonable than putting all 50 states together. We have seen that we could produce an average with the standard deviation in these error bars. And then we've also seen that we can use an approach called small multiples, where we put each one in its own cell or its own subplot. What I want to do is return to this and see if we can come up with a model that can account for the behavior that we're seeing here. Clearly, when you look at this, you can see that this is a nonlinear behavior. I mean, this average kind of does look like one line followed by another line, but with two different slopes. And we could try to fit this to two different sloped lines. I think that would actually work pretty well. But something else that we might think this approximates is exponential growth. And so what I want to do in this particular video is think about how we can create a model that is exponential growth and then fit that model to this data. So we're going to work primarily with this data here, which, to remind us, is the average by year. And so we're going to think about how to fit the average by year data to an exponential model. Okay, so what we need to do is first create that model. And when we create that model, we're going to use a library called lmfit. So I'm just going to go to the top here, and I'm going to also say from lmfit import model. lmfit is a library that does least squares fitting. So this is the typical sort of how do you fit a line to data or some sort of analytical behavior to data or even numerical behavior to data. And from it, we're going to import the model class. We don't have to worry about what a class is, but basically it's a part of this library that lets us define a model that we eventually want to fit to our data. Okay. So let's go down here. And the first thing we want to do when we have a model is we need a function that lets us describe the behavior that we expect. We're used to functions, right? Like if I said print 2, print is a function. It takes some argument, in this case 2, and it provides us an output, or in technical terms, returns an output. And so what we need to do is define a new function. And we do that by saying def, so define. We provide a name for the function we want. I'm postulating that the behavior that we're seeing here is exponential growth. We could call this anything we want, but let's just call it exponential growth. Then we provide the arguments that we expect to have. We want this to go by year. We want to have a function. Ultimately, we're going to add more arguments up here. I'm going to hit colon. We're going to make a control structure like we had when we had a for loop. And then I'm going to make sure that whatever year comes in is going to be an array. We already saw that we can convert like a list or something like that into array. So I'm just going to say whatever we provide, I'm going to 100% make sure this is an array. And then with that, I'm going to return a value, and it's going to be some scale. We're going to scale something. That something is going to be an exponential factor. We're going to have a rate times a year minus some offset. So our data starts at 1940. So we need an offset of the year to account for that. And then we're also going to provide some sort of starting value. So what this is going to do is it's going to take a number, and then we're going to take that exponent of that number minus offset times a rate, and then we're going to multiply that by some sort of scaling factor and add in some starting value. We need to have supplied all of these values. So in addition to year, we need to have a scale. We need to have a rate. We need to have an offset. And we need to have a start. What we're doing up here in this definition line is we're just telling this function, this is what you should expect. That we're going to give you a year or a set of years, a scale value, a rate, an offset, and a start. And then we plug them into this equation and provide that back. This is how you define functions in Python. And so every function you've ever used, whether it is printing, whether it is making subplots, whether it is adding scatter or updating traces, they all work essentially this way, where you have something where you've defined what you expect to use and then how to use it, and you return a value from that. You can see I spelled this wrong. Let's try that again. Okay. So we could invoke this just like we would anything else, right? If this function was print, then we would go print and put some values in there. Same idea, exponential growth. And what we need to do then in this exponential growth function is we need to supply a year, like this could be, let's say 1940. And then some sort of scale. I don't know, maybe this is 2, a rate. It could be like 0.1, doesn't really matter. Our offset is 1940 and our starting value is maybe like 2000. And if I run this, then you'll see I've output some sort of number, in this case, 2002. So I took this 2000 and the part that was the scale times the exponential rate year minus the offset amounted to 2. And maybe instead of starting at 1940, I want to know what would happen by the year 2000 if we did this. And you'll see I'll get a different value that's larger because this is exponential growth. Okay, so now we have this function. What I want to do is I want to convert this function into a model. And so let me call that exponential model. And that equals model. So the model class that I imported has a function called model that's going to give us a model object. Need to spell right, exponential growth. So we're saying take this exponential growth function and convert it to an lmfit type of model. All right. Once we have the model, what we need to do is use that to fit the behavior. And usually when we fit something, we have a series of parameters we're trying to change. Like if I was fitting a line to data, I would need to fit the slope and the intercept. Those would be parameters. And so I also need to create some parameters. So let's call this exponential parameters. And the model object that I created, this exponential model, comes with a method that is make parameters or make params. So this is going to basically look at this function here, and it knows that the first thing in that function should be an independent variable, and then we have a series of parameters after that. Once I have those parameters, then I can define them, and we're going to do this by taking these parameters and use a method of that, which is called add many. And then within that, we supply a series of tuples, and tuples are objects that are placed between parentheses like this. So what we do is we use a string to name our parameter. So here's scale. Then we hit comma. Then we press. Then we enter a guess. So let's say our scale is 1. We have no reason to think otherwise. And then we have one more parameter. In this case, it's true, which is telling us whether we're going to actually fit this or not. So I could say false, and it would be something we don't fit. Then I just go down and do the same thing again. Next is rate. So we have a string that says I have the rate parameter. Let's just also give this a value of 1. And then we'll say, yeah, I would like to fit this. So we'll say true. I apologize for my poor typing right now. The next thing is offset. So offset for us is the years basically that we started at. So 1940, that is 100% what it is. And we don't expect that to change. Like, this is a parameter that will not change. Our data starts at 1940. So this is somewhere I would say false, because I don't expect this to need to be adjusted. And then the last thing is start. This start value is like in the interpretation of this sort of behavior, this exponential behavior. What this start function is what was the housing price when we were at 1940? Okay. Essentially the housing price, and then of course we take into account what the scale factor is in the way that I wrote this. And there's many other ways we could write this exponential growth. I just thought this was the easiest one to understand. And so if we had average by year, now I want to know what is a value that I could guess to start. This average by year would be this first value. So it would be about $2,563. I could use that and just type it in, or I could realize that when I averaged out these columns, like the average by year is like the average of this column, the average of that column, the average of that column. And so it's the last column. So if this is 0, 1, 2, 3, 4, 5, 6, it's the sixth column. And again, remembering that we start at counting at 0. And so I could just put in for my guess here for what we start as 6. Something else you could do though is we realize it's the very last of the columns. And so something else we can do in Python when we want the last column is just to say -1. So it's like we start at the beginning and then we go backwards, and that wraps around to the end of the list, and that is -1. So we'll just use that as our guess, and we'll allow this to be fit. So now what we've done at this point is we have defined a series of parameters. Then we just need to fit our data. So if I say fit equals, we could fit this exponential model here. I could type it out, or I just copy and paste. What you do when you fit something is you use the fit attribute, fit method. And then you supply as the first argument the thing you want to fit to, and that is our Y data. So again, that's like the average by year. And so the first thing that goes here is average by year. And then we supply information about what our parameters are. This first parameter is like the independent variable, like the X values, and it's called year. So we'll say the year is years. If we go back up to where we started this entire notebook, we see that we define the years here is the years that we have. So I'll say that the year is that independent variable is just that years that we had defined. And then we could define all these other parameters, but because we made this model object, we can also just say that the params for this is these exponential parameters that we created. This will, when I run this, fit everything. So let's just go ahead and do that. I had a problem where we hadn't run this yet to import lmfit model. So I need to do that first. If you're doing this on MoLab, you may not have access to lmfit, and so you would need to go to the package manager again and then type in lmfit and install that. But we know how to do that now. So once I've installed the model, now I could run this again, and I will end up with a fit. If I want to know what the result of this fit is, there's a fit report, and so let's just print that. We'll take fit, that is, so essentially what I did was I fit the model to this data using these independent variables, and I assigned it to this. So actually I could look at this entire print fit object, and it's an lmfit model result. So this is the result of fitting. One of the methods it has is generating a fit report. And if I do this, we'll get the output, or sort of what happened when we fitted this, like what was the end result. And you'll see that our variables, what we were calling parameters, we have values for now. So it came up with a scale value of 1052, a rate of 0.04, an offset of 1940, but we didn't allow it to change, so it was fixed, and then a start value of some negative money. All right, we'll come back to that because that doesn't make a whole lot of sense yet, but let's plot the result first. And so we have a result. Let's see what it looks like. So we have fit plot, equals make subplots. And then we have fit plot dot add scatter. So the first thing I want to do is add the experimental data. And I want to basically make something that's just like this plot up here. So why don't I just copy all that actually? So here's add scatter. It's going to give me the experimental data and the errors. I already typed all that, so let's just put it there. All right, the next thing I want to do is add in the fit. So fit plot, add scatter again. And then what we'll do is we'll add in x equals the years. And then y equals, what I would like is the result of this fit. So fit, and then it turns out that there's also an attribute called best result. And so that's going to give us the y values that are the best, the result of the best fit, the best parameters, the ones that we're seeing up here. All right, and then I can say fit plot show, and if I plot this, not best result, I'm sorry, best fit. Then what you see is I have trace 0, that would be like the experimental data, and trace 1, that's basically the result of the fit. And you know, again, we could like handle this however we want. I could basically say show legend equals false here for both of them. Why not? I don't think we need this necessarily. So show legend equals false. This show legend equals false needs to go outside of the dictionary that is associated with the errors. So let's just put it down here. There we go. Clean that up. In order to make it clear this is the fit, what we might do is try to add an annotation that just reproduces what this function is. So this would be something like fit plot dot add annotation. We know that we can use f strings to include values in here, and so why don't we just say y equals, and then we could take scale. So putting this between these curly brackets, that will insert that scale value, for instance. But we want the best fit, and so what I would say is I want the fit result, I want the params, and then I would like to access the scale. Let's use a single quotations. And then I want the value of that. So now if I hit enter, what did I do? Add annotation f equals fit dot params scale value. I needed to tell this that this was the text associated with this. And so there we go. This was the scale value that was extracted. You can see it's the same as right here. Okay. I don't need all of these numbers. Like maybe I just want to get the stuff that's like without all the decimal places. And we can format something inside of this f string by pressing colon and then giving it instructions. So f would be like telling it that we're dealing with something that is a float. This is the technical term in programming for a number that has decimal places. So we would say, I want a float with like 2 decimal places. If I press enter, you'll see I now have this number that has 2 decimal places. Let's just say I wanted to truncate it so it's an integer. So 0 decimal places. There we go. And so now what you can see is I could do this. I could say I multiply this by an exponential. That exponential has a rate. So it would be this same thing, fit param scale value maybe 0 decimal places. But then if I look up here, I can see maybe I want actually 3 for this particular value to be able to see it. And then I need to not have this be scale. I need this to be rate. And then I also multiply this by, let's see, the scale, but not the scale. This would be the offset. And then years. So the year minus the offset. And then finally, I have plus this starting value. And so we'll put this in and we'll say this is starting. All right, so now, or start. Okay, so at this point now, what we have, I need to put these between curly brackets so that they are evaluated. I should basically express the function that I fit. And here it is. So this is in a bad place. I didn't tell it where I wanted it to be, so it put it at 0, 0. We know how to adjust annotations at this point. So I can say, I really would like this X to be at, I don't know, let's put it at kind of near the end, 2000. And then the Y value, I have an idea of kind of where it would be, maybe 120K. Okay, so we'll try that. It has this little arrow I don't want, so I know how to get rid of that. I can say show arrow equals false. We saw that in a prior set. And now this overlaps a little bit. So let's maybe adjust where the X is. Let's say maybe I really should put it at 1980. Probably it looks like even at 70 would be, whoops, 1970 might be better. If I want, I can control essentially the colors so that the color of this equation matches the color of the line that it was fit to. So let's make a choice about that. How about font equals dictionary, color equals red. And then when we add in the scatter that is the best result fit, I'll do the same thing. Line equals dictionary, color equals red. And now these two things are matched to one another. Maybe I would get rid of the points as well. So I would say here that we'll just use a mode that is lines. All right, now I have this fit result. I can move it down a little bit. Maybe I should really put this at like 80K or so. Good. Something that I don't like about this fit, now that we've sort of got it formatted and I can look at this and think about what's going on, is that the starting value is negative dollars. Doesn't really make sense. I don't think there's really been many times in the history of the world where people have been paying other people to take houses. Certainly that has not been the case from 1940 onwards. So this negative value doesn't make any sense. It would be nice if we could restrict the fit that we have so that we don't allow negative values. And in fact, when we go up here, this was start. This was the initial value. This was telling it that we should fit it. We can provide two more values, one of which is a lower bound. So if I put a 0, it means this can't go below 0. And if I say none, it means there's no upper bound. So these next two entries are whether there's a lower or upper bound. If I run this, it'll update down here and you can see that we have a value that is no longer negative. So now we don't have a result that's telling us that there was a time in the history of the world where people were just paying other people to take houses. And to me, that makes sense. We have created some sort of proximity in color that lets us associate this annotation with this line. We have fit a line that pretty reasonably explains the behavior that we see. And we have learned how to, in general, define a function that lets us then fit that function to data, get a report, and make a plot of that report. That's a pretty powerful thing to know how to do. And with that, I guess that's all I want to say in this particular video.